Hi, and welcome to Macom 316 for the fall of 2022. It's the occasion of the Queen's Memorial Service. So I'm going to record the lecture that we would have otherwise had today, and I'll put this on my YouTube channel, which is where, of course, you're seeing this. So you already know that. Okay, so what we're going to talk about today is a linear algebra review, matrix inversion, and finding a determinant of a matrix. I'm going to go relatively quickly because this is material covered in Math 232, which you have all taken. So we want to just make sure that we all recall how to do this stuff. So I'm just going to go through a few basics. One is that two matrices are equal if all of their entries are equal. They need to be the same size and all of their entries are equal. And then we say that the matrix is equal. To add two matrices, you simply add the entries in each specific position in the matrix to the one in the same position in the second matrix. We can see this easily with an example. We've got A and B here. Does A equal B? Let's take a look. No, it does not. A does not equal B because there's some entries that are not the same. So, for example, we have this problem right here. That does not equal that. So I mean, these matrices are not equal. The answer here is no. And then let's just add them together to form C. So C is going to be A, that is A, plus B. And I simply go and I add -1 and 1, I get 0. I add 3 and -4 and I get -1. And then I add 2 and 2, that's on here now, 2 plus 2, and I get 4, and then -4 and -3, I get -7. All right, so subtracting is the same thing, except you subtract rather than add. Just one thing to note, there is an identity matrix filled with zeros. We sometimes write it like that. And if I add the zero matrix to A, I get back A. So the 2 by 2 additive identity matrix looks like that. If I add A to it minus itself, if I think of it as subtracting A from itself, I get 0. I get the additive identity element. All right, so a couple of points. Matrix addition only defined if the matrices are the same size. Matrix addition, let's be careful about that because it's not going to be the case with multiplication. Matrix addition is commutative. Matrix addition is associative. It's pretty easy to do that, adding and subtracting. The next item on the up on the food chain is multiplying by a scalar. So a scalar, this is simply a number. Okay, so if you multiply a matrix by a scalar, then you multiply each element in the matrix by the scalar. So let's just take an example of that. Here's a matrix, 1, 2, 3, 4, and here's a scalar, lambda equals 10, and then I want to say what is lambda A, and that is actually the same as A times lambda, which is going to be 10 times 1, 2, 3, 4. Now I simply multiply each one of those elements, 1, 2, 3, and 4 by 10, resulting in this 10, 20, 30, 40. Okay, so that's multiplication by a scalar. I will just note that scalar multiplication distributes. So that means if I have lambda times the sum of AB, that will be the same as lambda times A plus lambda times B. If we have this case, two scalars like that, that is the same as lambda mu A. Like that. So you can associate in either order, and then we also have this case where we have two scalars added together, multiplied by a matrix, and then that one looks like this. It distributes. And the scalar 1 times A is A. Okay, that's scalar multiplication. Transposition. The transposition of a matrix, which when we transpose a matrix, we use that word there, transpose. I will typically in my lecture notes write it like this, the transpose of A, and that basically means the artist formerly known as the rows become the artist now known as the columns. Okay, so we basically make the rows into into columns, or we can think of it as making the columns into rows. Either way it works. So we're going to just do a bunch here. Here we've got A, there's A right there. So A transpose is going to look like this. First row becomes the first column, and then the second row becomes the second column. Okay, so in this case, actually, it is the case that A transpose is in fact A. Let us see one where that doesn't happen, because maybe that's not the best one to see right out of the gate. Let's do B transpose. So B transpose, I'm going to take the first row of B and make it the first column of the transpose. Second row becomes the second column, and the third row becomes the third column. Okay, so there's B transpose, and then C transpose. I'm going to do the same thing. First row becomes the first column, 1, 2, 3, 4, and the second row becomes the second column. That's how you form the transpose. This one, where we had A transpose is equal to A, the very first example, that's actually a special type of matrix, and we're going to see that's one way of recognizing a matrix that has symmetry. In this case, it has reflective symmetry, if you will, across the diagonal. In fact, that's what we say right here. A square matrix, it has to be square, is symmetric if A is A transpose. And then there's a few other things we could say about the transpose, and that would be that if I take the transpose and then I do it again, I get back to where I started. Okay, that's I take the rows, I make them columns, then I take the column and make it a row. I get back to where I was. If I take the transpose of a sum, that is equal to the sum of the transposes. If I take the transpose of a product of matrices, now we haven't really gotten to the matrix multiplication yet, but its matrix multiplication is not commutative, and so we're going to be careful about order here. This is like this, and the order does matter. Order matters. Okay. If there is an inverse, so we have a matrix. We're going to also see how to calculate inverse and talk about them a little bit more just a bit later on. But because we're here with the transpose, if matrix A has an inverse, and then I take the transpose of the inverse, that will be equal to the inverse of the transpose. Okay, that's so far now addition, scalar multiplication, and transposition. Now we're going to move to the matrix multiplication. You know, if you think while you're watching this, oh yeah, this is all review, I know how to do this, stop the video, do these examples yourself, turn the video on, maybe go through at double speed, and make sure that you got the same answer as me, or if I made a mistake, you've caught it. So you don't have to watch me do this if you already know how to do it. Stop the video and do it yourself. That's always better. Okay, so we're going to take C, and C is going to be the product of A and B. So here's A, 2, 3, 1, 1, 4, minus 1. We're going to multiply by B, minus 5, 1, 0, 2, minus 3, 4. Okay, now you can't always multiply two matrices. The sizes have to be correct. And so here we've got a 2 by 3 matrix. That's 2 rows and 3 columns. And we've got a 3 by 2 matrix. That is 3 rows and 2 columns. When you're multiplying two matrices together, these two inner numbers have to match. If they don't, you won't be able to do the multiplication. And further, the C, we now know because the two numbers that are left here, that C will be a 2 by 2 matrix. Okay, so the size is important here. Okay, so what do? We now take the dot product of the first row with the first column. That's how we're going to find the first number in the product. So I'm going to write this one out, and then I'm not going to write out the other 3. So what I'm doing here is I'm taking the dot product row 1 with column 1. That's the entry that's going to go right here. So that is 2 times minus 5 plus 3 times 1 plus 1 times 0. And that is minus 10 plus 3. So this entry right here is minus 7. Now I take the dot product of the first row with the second column, and then that entry is going to go right here. So that becomes 2 times 2, that's 4, minus 9, 4 minus 9, minus 5 plus 4, minus 1. This entry is minus 1. Okay, and then I go for the next one. I take the dot product of the second row times the first column. like that. -5 plus 4 is -1. This entry is -1. And then the last one, I take the dot product. I'll even do another color. Dot product of the second row and the second column. That is 1 times 2, -12, which is 3 times 4. That's -10, -4 more. That is -14. Okay, so there's the answer there. 2 by 2 matrix. That is the product of A and B. Okay, here, let's do a couple of more examples. Let's take C times right here, A times B, and A is 3, 2, 1. B is -5, 1, 0. And do the multiplication. I get here, well, I'm going to check the sizes. 1 by 3, 1 row, 3 columns, 3 rows, 1 column. These guys match. I'm expecting a 1 by 1 matrix. And indeed, that's what I get. And the number here is -13. Okay, now let me try to do it the other way. Let me try to find D, which I claim I might be able to do, let's call this D, as B times A. That would be here B -5, 1, 0, -5, 1, 0, 3, 2, 1. And what happens here? I can do this one. This is a 3 by 1. And this is a 1 by 3. These two inner dimensions match. Things are fine. And I'm expecting a 3 by 3 matrix. And so what I'm taking is the first row into the first column, -15. First row into the second column, -10. First row into the third column, -5, etc. 3, 2, 1, and 0, 0, 0. You have to be able to multiply matrices. We're going to be doing this all of the time. Okay, there's a bunch of ways of thinking of matrix multiplication. I sort of use the dot product. If you can't remember that, quickly look up what is the dot product. But I was thinking dot product of the first row with the first column like that. The other way of thinking of it is that each column of the product is a linear combination of the columns of A using the weights from the corresponding column of B. So you can take a look in the textbook, the formal definition. This is a highly important point. Matrix multiplication is not commutative. That means that AB is not equal to BA, unlike what we're typically used to and how numbers operate. And that fact that it's not commutative, this thing immediately follows from that. And this is where it's usually most students remember this well and won't just reverse the order. But sometimes people will make this mistake, not realizing that this cancellation law doesn't hold when you don't have commutativity. Okay, so be careful of that. It means that you cannot do this. If you've got AB equals AC, you cannot just go like this and claim that B equals to C. That is not correct. Okay. Also, you cannot conclude that if you've got AB equals to 0, that either A or B is equal to 0. Whereas if we had numbers and we had something like X times Y equals to 0, then we would actually conclude that either X is 0 or Y is 0 or both. We would be able to make that conclusion. We cannot do that here. So watch this statement. You must know, but watch that you don't just be so used to numbers and see the symbols and then just start crossing stuff out like you would, because that will result in error. No, for sure. Okay. There's a few other things we want to say here. If the sizes are correct, okay, because we can't multiply matrices where the sizes don't match up properly. But if the sizes are correct, then the following applies. A times BC is equal to AB times C. That multiplication is associative. That is one. Matrix A times the sum of matrices B and D is AB plus AD. That is a distribution. And then if we have, we've in fact seen this already, but if we have a scalar times the product AB, that's going to be equal to the scalar times A, then times B, and that's also equal to A times the scalar times B. So you can move the the scalar multiplication around. Diagonal matrix. Let's get a definition of a diagonal matrix. Diagonal matrix. That is, well, first of all, it's square. I could do that one. It's square. And two, Aij, the element Aij in the matrix is 0 for I not equal to j. That is the definition of a diagonal matrix. And so that it looks like this. Okay, there's entries just here along the main diagonal. A diagonal matrix is both lower and upper triangular. Okay, so it is both lower and upper triangular. Lower triangular looks like this. 2, 3. Let's just -1, 10, 6, 0, 0, 0. That's a lower triangular matrix. All the entries are on the diagonal or below. And an upper triangular matrix looks like this. There. Oops. Upper triangular looks like that. Okay, all the entries are below are 0. All the entries are in the upper part of the matrix up here. Okay, that is lower triangular, upper triangular, and diagonal. Identity matrix. This is important. The identity matrix I looks like this. 1, 1, 1. All ones and all the entries off the diagonal are 1. So the identity matrix has a diagonal, and every entry on the diagonal is 1, and every non-diagonal entry is 0. Now this is like the number 1. This is the multiplicative identity element, and it works like the number 1. Okay, that means if we, for example, take A times I, we will get A, and if we take I times A, we will also get A. Okay. When we multiply a matrix by the right-sized identity matrix, nothing happens in the sense that we get back what we started with. Okay, this now, once we have an identity, a multiplicative identity element, that allows us to talk about what is the inverse. Okay, the inverse is a matrix such that when you multiply a matrix by its inverse, you get back the multiplicative identity element. For number multiplication, let's just see the analogy here. For number multiplication, we have actually exactly the thing, but we haven't sometimes been as precise in our language when talking about numbers. But what we're really talking about is, for numbers, 1 is the multiplicative identity. That is because, for example, 5 times 1 is 5. When we multiply by 1, we do not change the number we're multiplying by. And also, we have the situation that the inverse of 5, not thinking of the reciprocal, and that means what number do I multiply 5 by to get the multiplicative identity element? And that is 1/5, because 5 times 1/5 is 1. So this is 5 times 5 to the -1 is the multiplicative identity element. So now, thinking of it like that, we see that this is exactly the same. We have a matrix. If we multiply it by another matrix and we get back the multiplicative identity element, then those two things are inverses of one another. Okay, so we don't right now haven't reviewed over how to find an inverse, but certainly we could check if two matrices are inverses, because if they are inverses, then they must multiply together to give their to give the identity matrix I. So to show that something is an inverse, I simply I think I also see that I made a correction here because they probably weren't when I first typed this slide up. So there, I've changed that to a -1.5. Okay, so let's now do that multiplication. 3, 1, 4, 2. I multiply that by 1 minus a half minus 2 and 1.5. Now let's see what happens. So I go 3, I take this dot product here, 3 minus 2, that's 1, that's good. And then I take the next into here, and I get 3 times, that's minus 1.5 plus 1.5, that's a 0. And then I come to this one, 4, 2, second row into the first column, 4 minus 4, 0. And then the last one comes out to be 1 as well. There, that's I. So that does mean indeed that A and B are inverses. Okay, for a 2 by 2 matrix, we can quickly get the inverse. For a 2 by 2 matrix. This is only for 2 by 2 matrices. You can get the inverse. Imagine we have a matrix that looks like this, A, B, C, D, and we want the inverse. I will just simply tell you at this point, the inverse looks like this, 1 over AD minus BC times D minus B minus C and A. Okay, a couple of things here. The number in the denominator here, this guy, that is called the determinant. We're coming to that next. And you see that, in fact, if the determinant, which I'm going to write it like this, if det A, the determinant of A is 0, then A does not have an inverse. So not every matrix has an inverse. Okay, we're going to be careful about that. Okay, if a matrix A has an inverse, it's unique. The inverse is non-singular, and the inverse of the inverse is A. Okay, this means non-singular means it has an inverse. I mean, we know that A inverse has an inverse because it's A, and we already know that A exists. Okay. If we have two non-singular matrices, these are matrices which have an inverse for which the determinant is non-zero, then we have this important relationship between the inverse of the product. Okay, we're just going to say something about singular right here. What does singular tell you about the linear transformation? So if somebody says a matrix is singular, that is telling you something. That is telling you that it does not have an inverse. But what does that sort of tell you about the geometry of what's happening? Well, we could imagine two vectors in the standard basis vectors, say in R2. We're just going to sort of take some amount of vectors in there, say the vectors in that thing. And the typical situation is we apply matrix A to all of those vectors, and we see what do they all look like once we've applied matrix A to them. Okay, so matrices operate on vectors and they do something to them, and then we're asking, let's see a picture of what happens with all of those, multiplying by all of those matrices. So something will happen. We don't know unless we know the numbers A, B, C, and D, but this thing will maybe look like this afterwards. And that was a linear transformation. Okay, so that is a typical situation, and this is A is non-singular. It has an inverse. So by multiplying by A, all of our vectors here get transformed and they look like that. And then if we want to go backwards like this, we would multiply by the inverse. Okay, that just is exactly like this. 3 times 2 is equal to 6. Okay, and then so we consider this to, like, in some sense, like our vector. It's not a vector, but I'm just saying in the thing here, we're taking the vector, and then here's our matrix. So we apply this matrix 2, in this case, it's multiplying by 2, and we get 6. Now 2 has an inverse, so we can take 6 and multiply by the inverse of 2, and we get back to 3. So these guys are inverses of one another. It allows us to go back and forth. Contrast that with the case where we would do something like this. 3 times 0 is equal to 0. And then we're like, oh, hey, we want to go back. 0 times what is equal to 3? There's no multiplicative inverse for 0, so we can't get backwards. And so that doesn't work. So, and you see that 0 does not have a multiplicative inverse. Nothing times 0 is equal to 1. Okay, what does that look like? This would be the singular matrix case. We still have all our vectors over here like that. We have all of our vectors over here, and we multiply them all by A. And what happens is, rather than getting something that is two-dimensional over here, we get something that looks like this. Okay, we get a loss of dimension. Now we have a one-dimensional object over here, so there's a loss of dimension. And then this is not possible. We can't go back. Okay, completely analogous to here, where after we've multiplied by 0, and somebody says to us the answer is 0, and then they say to you, what number did I multiply? Like if I said the product of two, I multiplied some number by 0 and I got 0. What number did I multiply by 0? You'd go, I don't know, I can't tell. And it's the same thing here. You cannot now go back. You've lost information when you multiply by a singular matrix, and you cannot get back. Okay. All right, so how do we find a matrix inverse? Well, we know how to do it for the 2x2 case, and we can use Gaussian elimination to do it in other higher 3x3, 4x4, 5x5 matrices. So let's go through that. This will also serve as a bit of a review for the Gaussian elimination. So again, if you know how to do this, stop the video, do it yourself, and then run the video at double speed and make sure you caught all the details. Okay, so the first step to do that is, what we're trying to do is find this matrix inverse. We want to do this by Gaussian elimination. Step 1, write the augmented matrix. Okay, that looks like this. Okay, and then you use Gaussian elimination until A is changed into I. When that happens, then I will be changed into A inverse. Okay, let's take an example. We'll just do it by a 2x2 matrix because it's fast. We of course could find the inverse of a 2x2 as I did on the previous page, but we'll do it this way. Okay, so the thing to do here now is to start using Gaussian elimination. We want to make this thing here a 0. What operation are we going to do? We're going to take E2, that is this, row 2, equation 2. We're going to add to it 1/2 of equation 1, and we're going to put that back in as equation 2. It's 2, so equation 1, row 1 is not changing, and then this becomes 0, 1/2, 1/2, and 1. Okay. Then I look, and my next step is there's more than one order you can do this in too. You don't always have to do it exactly the order I'm doing, but I'm looking at that. I'm going to say, oh, that guy needs there to be a 1. I'm trying to make this look like I, so I need to get a 1 there. So my next operation is going to take 2 times E2 and put that back into E2. That gets me this thing here, 2 minus 7, 1, 0, and then 0, 1, 1, 2. All right, next thing, I see that this guy here needs to be a 0. So how am I going to get that guy to be a 0? I'm going to take the first equation, and I'm going to add 7 times the second equation to it. I'm going to put that back in as the first equation. That gets me this here, 2, 0, 0, 1, 8, 14, 1, and 2. Okay, I'm getting close. This thing needs to be a 1. In order to do that, I will take 1/2 E1 and put it back to E1, just multiplying E1 through by 1/2. So this is like that. That is going to be 1, 0, 4, 7, 0, 1, 1, 2. And then this is now I. So I stop, and I know now that the inverse of the matrix that I started with A is 4, 7, 1, 2. Why don't you check? Multiply A times A inverse, make sure that it's I, multiply A inverse times A, and make sure that it's I. Bit of practice with multiplication as well. Okay, so that is finding an inverse using Gaussian elimination. The next thing we're going to talk about is calculating determinant, and that determinant tells us about the existence and uniqueness of a solution of linear systems. And you can take a look at page 896 of the Burden-Ferris textbook for the computational procedure. And so there's some important points about the determinant. That is, if the determinant is non-zero, that's a big one. Whether or not the determinant is 0 is telling you something about the matrix. If the determinant is not 0, then there is an inverse, and this guy has a unique solution. And then here's another fact about determinants. If you have an upper or lower triangular matrix, then you just have to multiply the diagonal entries. Let me just give you an example of that. Here's a diagonal upper. Here's an upper triangular one. 1, 2, 3, 4, 5, 6, 0, 0, 0. So as soon as you deduce that it's triangular, now if you want to know what the determinant of that is, we put the bars here like that. The determinant of that guy, that is going to be 1 times 2 times 3, the product of the diagonals. So that's 6. It is also the case that the determinant of a product is a product of the determinants. So some of these rules that we've been seeing about the transpose, about the inverse, about the determinant, these things allow you to do calculations sometimes more efficiently. Sometimes you might be thinking to yourself, it's expensive to multiply together A and B, but I only really want the determinant. It's way smarter than to calculate the determinant of A and then calculate the determinant of B and then multiply them together, rather than doing matrix multiplication, which can be an extremely expensive operation. So there's times when we're going to be using these rules in order to be smarter in terms of the efficiency of our operations. Okay, so as before, if we have a 2x2 matrix, we have a 2x2 matrix looking like this, A, B, C, D, and we want the determinant of that, we just go like this, determinant of A, and we simply multiply the main diagonal there, A times D, and then we subtract the product of the other two numbers, B, C. So it's AD minus BC. For larger matrices, and by hand, we use cofactor expansion. You do not use, MATLAB does not use cofactor expansion for large matrices. Okay, in fact, it's a good idea to always keep reading the MATLAB documentation and say to yourself, what would MATLAB do? A lot of thought into how they do these operations. So take a look at the documentation for finding the determinant, and then read what it says. It usually tells you what method it's using, and you can learn actually a lot from that. Okay, so let's do one that we would do by hand. We'll take a 3x3 matrix, 2, 2, 0, 2, 1, 1. -7, 2, -3. Okay, so what we're going to do is we are going to do by cofactor expansion. Now, this is just a simple single example. If you are rusty on this, you can't remember how to do it, certainly do more examples than this and read through the textbook and think about what you're doing. Like, do enough practice so that you've got this skill back. So the first thing I'm going to pick which row or column to do my cofactor expansion along. I always pick the row or column with the most number of zeros because I find multiplying by 0 quite easy. So I see that there's a 0 in the first row, so I'm going to pick to do my cofactor expansion along the first row. So the determinant of the matrix A is then, and then this number here, 2 times the determinant of what is left if I cross out the row and column that number 2 is in. So that gives me the determinant of 1, 1, 2, minus 3. And then it goes like this, plus, minus, plus. Again, for some of these details, make sure you recoup those back. It's always alternating signs. So then I'm going minus 2, and I'm looking at this number here, also a 2, minus, that's where this 2 is coming from, minus 2 times the determinant of what's left if I cross those out, and that is 2, 1, minus 7, 3. And then I move to the next number, and it's plus 0, and then I feel happy. I don't even fill this in, right? Because I got this 0 here. I don't even have to worry about that. That is going to be 0. Once I've got it, once I've got it down to 2 by 2 matrices like this, then I can simply use the AD minus BC. So I'm here and I use the formula for the 2 by 2 determinant, which is 1 times minus 3 minus 1 times 2. So that is minus 5. And then minus 2 times the determinant of this matrix here, which is 2 times 3 minus 1 times minus 7. So that's going to be 6 plus 7. Hang on. Did I get this right? Minus 7. No, I see there's a minus 3. Oops. This minus 3. There's a minus sign missing right there. Apologize. Let's get that in there. So now it's 2 times minus 3, which is minus 6, minus 1 times minus 7, which is plus 7. So this number here becomes a 1. And I have here then, oh, and then there's a plus 0. We already knew that, but let's put it in there. That's this guy here, plus 0. So that gets me minus 10, minus 2, a determinant of minus 12. Okay, you can try this out in MATLAB. You simply enter the matrix in this manner right here, 2, oops, not a comma, 2 space, 2, 2, 0, semicolon, 2, 1, 1. So that's first row, second row, third row. You tell MATLAB, what is your matrix? There it is, single line. And that you sort of would enter that at the chevron. So this is the MATLAB doing it for you, MATLAB. And then you simply, there's the chevron, you simply say D, E, T, T, and then coming to the chevron is the number. There. Okay. So there you go. That is how you find a determinant. And that, in fact, concludes our lecture here for 6.3 and 6.4. I'll see you in class shortly. Thanks, guys. Bye.